That is the program. It's a program. So it is 7th program in the lab cycle. Seventh program. Okay. So Dijkstra's algorithm to find the shortest path. So we have to, from a given vertex in a weighted connected graph, we have to find shortest path to other vertices using Dijkstra's algorithm. Okay, and we have to implement it by using Java. Write the program in Java. That's what the complete question is. Write the program in Java. Fine. Okay, so let's start the program. I'll be taking attendance thrice. In between also I'll be taking. I just want to check how people are. Once attendance is taken, they'll just move away from the session. So in between I'll be taking. So what is this? We will obviously use this in order to scan. We have those scanning statements, hence we import this, and we will start with the class. I'm audible and the screen is also visible, I guess. Right?
Yes, ma'am.
Okay.
Yes, ma'am.
Yeah. So Dijkstra's, we'll just take it as a Dij. Okay, Dijkstra's, and the variables we will just public, static, void, main, and we have string marks, isn't it? Then we'll start. This bracket you can write it here also. This bracket you can write it here also. Usually the practice is that they will write it there. So we have scanner, the variable, and scanner system dot in, isn't it? So these are the things what you have to generally do after when starting the program. So you will have one scanner system dot I dot in. Then we will check what are the variables which needs to be declared, and we will just declare those variables. Okay. So we have, what are the variables we need? We need one. You finished class? Okay, we have int the cost matrix, isn't it? Because you know that Dijkstra's algorithm will have a cost matrix. Because the input for the Dijkstra's algorithm is a cost matrix, isn't it? We have to find the shortest path. Now, we need an array called as visited. This is just to check, like you should not visit a particular um, vertex again and again, isn't it? Once if it is visited, it should not be considered for the next visit. Once it's already done. So we will use one visit array to keep track of all the nodes which are visited. But manually while doing, we need not, because we will use our knowledge and we will find out that okay, 2 is already done, we will not go for that. But while writing a program, we should also take care of not revisiting the nodes. For that, we will have one visited. In the same way, we'll use this concept in prims and crystals also while writing the program, because we should not form cycle, isn't it? We should not form cycle. When do we form cycle? When we revisit a particular vertex, isn't it? Is that clear? So if you are starting from 1, going to 2 and coming back to 1, this is a cycle. So this means 1 is revisited. We should avoid these cycles. We need only shortest path from 1 to all other vertices. But whereas TSP, we need a tour. It's a tour. You remember TSP, whatever we discussed yesterday? Yes? TSP is done, isn't it? You know what
Yes.
is TSP? Yeah. TSP is what? What is TSP? Yeah? What is traveling salesperson problem? What is traveling salesperson problem? Telling you, put in your own words. What is traveling salesperson problem? Yes. Someone? Boys? Some boys can answer for this. What is traveling salesperson problem? Yeah? Okay, they're putting it in the chat box. Oh, that was earlier reply. What is TSP? You are behaving as if you have not heard that word at all. TSP? Rakesh? See, there are 48 in the meeting. Dhananjay, Bhargav. I know girls, if I will call, they will answer. I want some boys to answer for this. Datapir, Preetam, Shivraj, Jashwant. Someone tell me what is traveling salesperson problem? I want replies from boys only. Fast. Hello? No one is there. So I'll mark absent for all the boys. Girls? What is traveling salesperson problem? Finding minimum.
Finding the minimum score.
What do you mean by a 2?
It's a simple path that starts and ends at vertex.
At the same vertex, isn't it? So, yes, it is the shortest path wherein we start from a source, visit all other cities or vertex once and come back to the city from where we started our tour. We form a cycle there. Whereas Dijkstras, do we need cycle there? Do we need
No,
cycle?
ma'am.
There should not be any
No,
cycles.
ma'am.
Yes, isn't it? There should not be any cycles. That's the reason why we have this visited. Okay, that's the reason why we have these visited array to take care of those cycles, because we don't need cycles over here. In prims and crystals and Dijkstras, we will use this array in order to keep track of all the nodes which are already visited, so that we will not form a cycle. Okay. Yes. Okay. So moving on. Next, we were just writing the arrays, and now we will have, so it's a single dimensional array. New int, it's a single dimensional array, and I have one more array, the distance array, and this is again a single dimensional array. And the variables whatever is required, the variables whatever are required are int have, so we have int I jk, this is comma, it's not, so we have I jk, and we have the source vertex. You will be in need of this w, n, and minimum. Okay, one second. Okay, okay, so we will have these variables declared. Now, once you are declared with this, we just ask the user to enter the number of vertices. This is based on graph, isn't it? We need a graph for this, and as you all know, graph always contains vertices and edges. So let us ask the user to enter the number of vertices. Out dot println, enter the number of vertices, and we will just scan it onto the variable n. Okay, now next, after that we need a cost matrix. We have to find the shortest path from source to every other vertices. So let's input the cost matrix, that is the cost between each edge, each pair of edges. Enter in the graph, whatever graph we will take, that cost matrix we will just give it as input. So cost matrix is a two-dimensional array, and we need two loops, I less than or equal to n number of vertices, and I also need an inner loop. This is for row, this is for column, and cost of ij equal to next int. Okay, we are scanning the cost matrix now. So now we know how many vertices are there and what is the distance between every pair of vertices, or whatever vertices are there in that particular graph, their cost matrix have just input. We have input using these statements. After that, what's the next step? We should ask the user to enter the source vertex from where we have to calculate the shortest path to every other vertices. Okay, so we will just ask the user to enter the source vertex, right? Hope you all are listening. So that we will take it on to this
Yes,
variable
ma'am.
source vertex. Yes. So we will just take that into this vertex. Next, int. Right. So we are done with the matrix and we have also chosen the source vertex as well. Next, after that, what we do is next, we will just make all the nodes in the visited array. For each node, we will just initialize 0. Once it is visited, we'll make it 1. We are just trying to distinguish which are the nodes visited and not visited by using the values 0s and 1s. Initially, no nodes are visited. Hence, in the visited array, for each node, we'll just put 0. At the same time, we will also copy the cost from. You know that initially when we start with the program, we have to have the path from source vertex to every other vertices whichever is reachable. So that also we will just take care by using the loop. Okay, I'll open the notes so that isn't it if we will look into this, then we will also have Dijkstra's. Was in third module or fourth module? Third module. 1 second. Yes. See here, if you will see here, first we have to note down the nodes which are reachable, isn't it? So we will just put visited as 0 and we will also copy. See, from A to B we have direct path and A to D we have. Others are infinity. So this first step we are doing it by using this statements. Okay. So we will just have a for loop where we will just make all the, we'll take a for loop from 1 to n. So what is this array visited? None of them are visited right now. So we will just keep it as 0. And what am I doing? I am trying to find out the direct path from 1 to the source vertex to different vertices. Source vertex to different vertices which are reachable and taking their cost and keeping it in a distance variable. Okay. So this is the first part I am doing. So what did I do here? I just made this all nodes as not visited and then whichever node was reachable from the source vertex to every other vertex, their cost I've just kept it in distance of I. Now we are starting the program now. We are starting to write the program. As you all know, first we are starting from the source vertex. Hence, I will make the source vertex as 1. What does this mean? Source vertex is visited. If you have taken 1, I am starting from here. Now I visited this, so I have just put 1 for this. This is the source vertex. So in whatever the graph, whatever we had, we have just taken that. So as an example, I have this. We are having number of vertices as 4. And the cost matrix, whatever we have given is, if there is no path, we have just kept it as 999. So this is actually the graph. This is the cost matrix, whatever we have. So 5, 3, 2, 999, 3 and 999. You can just write down the graph for this and keep it. So source vertex is 1. We have to find shortest path from 1 to every other vertices. Okay, this is 1, 2, 3, 4. 1, 2, 3, 4. So 1 to 1, 0. 2 to 1, we have a path with cost 1. 2 to 3 or 1 to 3. This is an undirected graph. 1 to 2 we have path, 1 to 3 and 1 to 4 also we have path. We need to find the shortest path from 1 to every other vertices. Okay. So what we have done here is we have just copied, we have first made all the vertices as not visited. Then we took from 1 to every other vertex, whatever cost we have just noted down here. So in this case, what happens? From 1 to 1 infinity, 1 to 2, 1, 1 to 3, 5 and 1 to 4. So that will be recorded here. Now as we are starting with the problem, the source vertex is visited now. So we are starting from 1. Okay. Now distance of this source vertex, we will keep it 0. Okay. Now we'll start from the second vertex. So k less than or equal to n, k plus plus. So minimum value, we will just keep it as 9994. Later it will change depending on the problem, on the condition, the minimum value will change obviously. So initially we'll take it as 999 for comparison. Now what we do is, we now start visiting the nodes. So let's take one more loop for that, because to access the array elements we obviously need loops, isn't it? Now we'll check the condition. If visited of w equal to 0. What do you mean by 0 instead of w? 1 is the node 1 visited. We are just checking. If 1 is equal to 0 and the distance of this w is equal to minimum, then if it's not visited and if it is lesser than the distance of w is minimum, that is it's not reachable, in that case we will just say, or if it is minimum, we just say that minimum distance is that distance of w, and then we have to just change this to u, so that the node whatever you have visited, you just keep it in u and make it as visited next, because this node is visited. W, if it is minimum, that's the next path, minimum path whatever we have put that into minimum value, and I have to make this as visited as well. So I'm just copying it onto another variable, and in the next sentence I'll just make it as visited. If it is a minimum distance, it means that we have already visited that particular vertex. Why we are taking care of this? In order to avoid cycles. We have just used this in order to avoid cycles. So we have this. If it is not visited and if its distance is minimum, we are taking in one vertex and we are checking whether, so the main logic which is followed here is, we are taking one vertex, okay, and we are first checking whether it is visited or not visited. If it should not be visited, because we are trying to find the shortest path. So if it is already visited would have been 1. So as we are starting now, it will obviously be 0. And if that distance is equal to minimum, then we will just change it. that becomes the minimum distance and that node becomes visited. Okay, this is just to avoid cycles. And after that, we have to just compare the distance now. You know, we compare the direct path with the alternate path. So how do we do that? We have this comparing. You know very well that we will compare using the formula. So we have this W. If visited of W equal to 0, that means if it's still not visited, then we just check the cost, whether distance of U plus cost of U to W, if it is less than distance of W. So whichever is less, that will be our new distance to W. So if this is less, then distance of W will become distance of U plus cost of U and W, right? If it is the minimum distance, then we'll take that as the minimum distance. So we are closing here. That's all. This is the main logic which compares the distance and takes the shortest path onto this variable, onto this array distance of W. So distance of W is the one which will hold the shortest path from one to every other vertices. So this is the main thing here. Once this is done, we have to just print the output. System dot out dot. We know that we have the output in distance matrix. We will just print it. That's it. So this is just for formatting. It's not necessary that you should do all these things, but it's better to format your output properly so that it will be nice to look at if you will format your output. So all these things, that's it. Otherwise also if you show the output, it's well and good. But formatting is also one of the important things. So we will just display. We will have source, destination and the cost. And we'll take a for loop and where is actually the minimum distance stored? It is stored in distance of 5. That's it. So source, what is the source vertex? We have it in SV variable and we are just formatting. Plus now we will leave some tab space and we will have I source to destination. Okay, and we will have this tab space again plus the distance of I. This is the cost. This is source, it prints destination and the cost. So it starts from 1. 1 to 1 is how much, 1 to 2 is how much, 1 to 3 is how much, and 1 to 4 is how much. That's it. Okay. So we have this printed. Here main closes and the class Dij closes. Once you run this program, you will be able to get the shortest path according to this. This graph is pretty simpler. graph is pretty simple. Here only you can tell the shortest path. It's nothing but 1 to 1 it was 0, 1 to 2 it is 1, 1 to 3 it is 5, and 1 to 4 it is 2. See here, if you will check here only in the graph, you may say, ma'am, here one more value is there, 3. Why you are not taking this into consideration? Just check this. 3 to 4 is 3. But already we have shortest path to reach from 1. Okay, we are interested in finding the shortest path from 1, and the shortest path is already available here, even though there is a path here from 3 to 4. If you will consider that, it increases the cost itself. So we will just, when you run this program, we will just have the output as, we'll just check this in the compiler now. So what did we do? We just did the, in order to avoid cycles, we are having this visited array, and initially we'll make it 0. Then we will just put all the distances in this from 1 to every other vertex. What distance is available, that is kept in distance of I. If you will observe, this distance of I here will have, see here, 1 to 1 it is 999, and 1 to 2 it will be here 1 to 2. Okay, 1 to 2 it will be 1 will be saved, 1 to 3 5, 1 to 4 2. Already distance matrix will have these values. Then what we do, we'll make the source vertex as visited, first source vertex is visited, and the distance will make it 0. The distance of source vertex will make it 0. Earlier it was actually 999, so we'll make it 0. Okay, then we'll start from the second vertex. We'll move on. When we check, vertex of 1 is equal to 0. Visited of W is 1 in this case. Is it equal to 0 in this case? Is it equal to 0 visited of W? No, the 1 is already visited, isn't it? That's the source vertex. So this condition fails. It takes the second vertex here, 2, and it comes here. Now, visited of 2 equal to 0. Yes, isn't it? Visited of 2 is equal to 0. The second node is not visited. And distance of 2. One second, I'll just check this. Double equals or sorry, this is less than minimum. That's what. One second, I'll just erase this. While writing, it's a mistake. Sorry for that. Yes, if distance of W is less than minimum, then that distance will take. Let's check here. Distance visited of 2. Second node is not visited still. Okay. And distance of 2, is it less than minimum? See here, minimum is 999. Distance of W is how much? Distance to 2. Distance to 2 is 1. Look here, 1. It's obviously less than this 999. So what is my minimum distance now? It becomes 1. So minimum distance becomes 1. And this U is actually 1. I'll call it as a parent. So U is now WW. Okay. Now U is 2. Okay. Next, we'll move on now. This, we are just moving here and we are checking. The W becomes 3 now. We check. Visited of W. Okay, 3 is not visited. Let me check distance of 3. Is it less than this 2? No, this condition fails. Again, 4 is not visited and distance of 4 is, minimum distance is 1 we have, distance of 4 is 2. So this condition again fails. So it comes here, next it comes here and checks if visited of W equal to 0. Visited of W is it's not 0 here. So it will just move on to the this. Again K becomes 3. That means that we have selected the shortest path from 1 to 2 as 1. So this whole thing has selected one shortest path from 1 to 2. Now k becomes 3. It's again repeated in the same way, and finally when it comes out of this loop, it would have got all the shortest path from 1 to every other vertices. So here it just compares the distance and checks if there is any alternate path here, then it checks. If it is not visited, it will just check whether the distance which is already available is lesser than the new route whatever is available. If it is lesser, then we will consider that. So finally when you come out of these loops, you will end up getting the shortest path from 1 to every other vertices, and we are just printing it. You know, sources at SV, destination is I. Like we have to find from 1 to 1, 1 to 2, 1 to 3. So we are varying I. So that is only displayed here. And then we have the distance matrix, which holds the shortest path, the distance from 1 to every other vertices. Okay. I just show the execution of this for you all in the compiler. Let's check that. One second. Okay, one second. I just run the program and show you the output. Meanwhile, you keep tracing the program. Trace the program for the next iteration. We did for one, right? So you just try to do it for the other. Next iteration, you just keep trying. Let me just show you the execution. I just keep program and just. Those who have systems, they can also try. Those who have systems. If you will not try, you will never understand. You should do mistakes and you should learn. If you are not trying, then you are the losers. That's it. Exams are nearing. Be serious from now onwards. Yes, I am. Okay, keep trying with the program. I'll show you the execution. I'm just doing it here. For the next iteration, you have tried. Share the screen. Got some errors. So I'm just debugging it. Okay, let's check. Error line number 67. Extra brackets, I'll just check. Yes, we will just go and give the input. So we have the number of vertices as 4, cost matrix 1, 5, 2, we have 1, okay, then we have 5, not reachable, 2 we have, 3, just entering the cost matrix, so over 1, 2, 3, 4. Now I'll enter the source vertex and I will yes, look here, we got the output as 1 to 1 it is 0, so 1 to 2 the distance is 1, 1 to 3 the distance is 5 and 1 to 4 the distance is 2. Okay, so for the program Dijkstra's algorithm we have got. Can you tell me some other matrix whatever we have solved in the class? So if you will tell me the values here, then instead of infinity we'll be using this 999, zeros and infinity we'll be using this 999. If you will give the input